But I had to take a moment to talk about some stats in the news. I don't do this enough. But show you how things that we're learning in here are applicable in the real world. It's amazing, right? Well, I saw this headline yesterday, and I read a little further. So, an article on NPR. Check out the whole thing there. The title is, "Can Mathematics Find the Missing Malaysia Jetliner?" Mathematics can do anything, right? So certainly it can also find the jetliner. Anyway, this quote here, there are thousands and thousands of square miles that need to be combed, and this is where statistics might help. And so my ears perked up even more. And then they're interviewing this person, Colleen Keller, who's a senior analyst with Metron Corporation, which is a company that uses mathematics to find things that are lost underwater. And so how does she do this? This is kind of a funny quote, I think. It's an actual mathematical theorem called Bayes' theorem. And of course, we all know what Bayes' theorem is, right? So they don't say a whole lot more in the article about kind of how they actually do that. Although I would recommend checking the article out. But I thought I'd real quick go through here and show you guys how we maybe could use Bayes' theorem to find the missing jetliner, or maybe something like what they would do, what this Colleen Keller person is doing to locate the jet. Okay, so this has been a long time, I know, but remember that Bayes' theorem, if we have certain events A and then a bunch of events B, I, so I equals 1 up to n, that's Bayes' formula, right? So again, we could talk about what that is, but the important things in here are the probability of A given the BI events, and then also the probability of the BI. So if I know those things, then I can calculate this thing over here on the far right. So anyway, those are the things that we need to use here. So in this setting, one way to maybe put this in the context of a searching type of a problem is if I divide. So I have my large region of ocean that I need to search, and I can divide that up and maybe put a grid over that and divide it up into some sort of a grid where I have n total grid boxes. So maybe it's 10 by 10, and then I have 100 grid boxes that I'm looking at. And we can set up some terminology here. Let's let BI equal the event that the plane is actually located in the grid box, in the ith grid box. And again, that's something we don't know. If we knew where the plane was, we'd be done. But we don't. So just for some notation, let's let that be BI is the event that the plane is actually in that box. And then let's define A to be all the information that we have observed so far. And so this is maybe a little abstract, but this information could be a lot of things. This is why this is kind of useful, because you can combine different sources of information. So we have information from radar. We have these pings from the black boxes. We have already searched some areas, so we know where the plane is not. There'd be a number of other ways that we could have information about sort of where the plane is or where the plane is not. So let's just call A to be all the information that we have observed so far. So that's a little abstract at this point. So then, kind of before the day's search, or before you start the search, you could set up some probabilities here for these events. So, sort of before we start the search, we maybe have some knowledge about where the plane is, or maybe we just sort of say it's equally likely to be in any one of those n grid boxes. So sort of my prior probability on where that plane is located could be sort of I don't really have a lot of information, so it could be something like 1 over n. Although maybe you also again know some of those boxes definitely don't have the plane because you've already searched them, so you could make some changes there. And then this thing down here. Probability of A given the BI. So that's the probability that of observing the information that we've observed. So we have all this information about where the plane is, or where the plane is not, maybe. And so we want to know what we could set up. You could set up a model that tells you what's the probability of observing the information that I have observed. If the plane was actually in a particular grid box, what's the probability of that happening? Of observing the information that I've observed. And here, this is something that's determined by expert opinion. So that's what this Colleen Keller, that's what she's good at. She can tell you, if I have some information, so suppose the plane is actually in a certain grid box, does that make the information that I've observed likely or not likely? So anyway, that's a little bit of a can't say as much about that anyway right now. But if I'm able to have both of these numbers, then when I can use Bayes' theorem to kind of flip those around. So using that information, I can find the probability that the plane is in a particular box given the information that I have, which is kind of what you'd want. You'd want the information that you have to sort of inform the probability about where the plane is. And again, we can do that using the information that we just looked at on the previous slide, as well as Bayes' theorem tells us how to actually do the calculation. So then as you continue the search from day to day, the information that you have somehow increases in a sense. You're gaining more information as you go from day to day, and you can sort of iteratively update these probabilities and kind of use areas that have high probability that you've calculated here to kind of maybe you could start your search there, and identify regions that are likely to contain the plane. So didn't want to bog you down too much, but I thought this was a cool example of how something that we talked about in here is being used in the real world. If you want to talk more about this, I'd be happy to maybe say a little bit more about this, but I just wanted to draw your attention towards this. Any questions or comments? No? Okay. Well, that's all I'll say about that, but anyway, I thought that was kind of cool. Okay, so we're going to resume our discussion of Chapter 8 today, talking about hypothesis testing. And we'll pick up on, I think, page 2 of your notes here in just a moment. But just to remind you kind of what we're talking about here, at the beginning of class on Monday, we introduced this example of the manufacturing process. And the company needs to decide. Remember, they're trying to figure out if their manufacturing process somehow needs tuned or adjusted, and so they have collected some data, and they come down the need to make a decision. Yes, I need to call this expensive engineer to come fix my manufacturing process, or no, I don't really need to do that. And so this led into our idea of hypothesis testing. So we talked a little bit about determining the hypotheses, and I wanted to say just another note about that. So when you're in the framework of this class, but sort of as a scientific method in general, I think when you're asking a scientific question, you always it's good to have a framework for which to test that within. And this is kind of a more general form of that, and we'll use a more specific form. So in general, in statistics, we call these things, we have special names for them. We have the null hypothesis and the alternative hypothesis. So again, as we discussed on Monday, the alternative hypothesis contains is sort of the claim we're trying to prove, or sort of the question that we want to answer. So in the previous example, the company might want to know, is my manufacturing process broken? So the alternative hypothesis would say, yes, the manufacturing process is broken. And then the null hypothesis and the alternative are kind of opposites in a sense. So the null hypothesis is sort of the opposite of what you're trying to show. You're going to start out by assuming the thing that you want to show is not true, and then see if there's any evidence to show that it is actually true. So we have these two hypotheses, the null hypothesis and the alternative hypothesis. And now, sort of thinking more about a statistical framework here, we're going to, for this class anyway, our hypotheses are going to be corresponding to something about a parameter, a population parameter. So here we're testing something. We're testing a claim about theta, which is a population parameter. And our null hypothesis will always be that that population parameter, maybe it's the mean, maybe it's the proportion, maybe it's something else. is equal to a particular value. So in the manufacturing example, null hypothesis is that the true average distance that the machine punches the holes from the edge of the paper is 8 millimeters, or is 7 millimeters, or is some number there. And that's something that I as the experimenter choose. Something you get from the problem. So then we have three possibilities for the alternative hypothesis, and that's going to depend on. This will depend on our question of interest. So. Depends on the question of interest. So either I want to see instead of the parameter being equal to some value, maybe I want to know if it's less than, maybe I want to know if it's greater than, maybe I want to know if it's just not equal to, it's different from, or something. Okay, and so we talked a little bit about setting up these hypotheses, but then at the end of the day, we want to make a decision, right? We're trying to decide, like in the example, either yes, I want to call the engineer, or no, I don't want to call the engineer. And so our conclusions that we'll have from these two hypotheses, we're going to sort of select between either the null or the alternative hypothesis. The terminology we'll use in here is we're either going to reject the null hypothesis or we're going to fail to reject the null hypothesis. And again, we had a little discussion about this on Monday. It's kind of the same idea as if you're in the legal system and you're being on trial. You're on trial. You're either guilty or not guilty. You're never declared innocent. So we're never accepting anything. We're always just rejecting or not rejecting. And so I will reject the null hypothesis in favor of the alternative if the sample evidence that I've collected sort of suggests that that's the right thing to do. So I want to make this decision based on data or information that I've collected, and so that leads us to a question of how do you decide what conclusion to make, and that's what we're going to talk about today. Okay. Any questions before we move on? Kind of remember where we're at here. Okay. Okay. So yes, again, sort of moving through our steps here for hypothesis testing, sort of conceptually. You start out thinking about what parameter is it that I'm interested in here? Is it the population mean? Is it something else? I can set up my hypotheses of what my claim about that parameter is. Again, I'm going to observe a random sample. I'm going to get some data. And then my next step here is I'm going to perform the test procedure. So what do I mean by that? Okay, so some new terminology. A test procedure is a rule, and that's going to be based on our sample data for deciding whether or not we can reject the null hypothesis. Okay? So this procedure here is again sort of a systematic way for me to use data that I've collected to answer a question about the parameter that I'm interested in. And so this procedure is going to be specified by something called a test statistic, which is simply a statistic that I'm going to use to either reject or fail to reject the null hypothesis. So kind of saying the same thing a few times here. But the point is that I'm just going to calculate something that will tell me that I can use to help decide, do I want to reject the null hypothesis or am I failing to reject? So that's all that the test statistic is here. Okay, so again, kind of motivating this thing, going back to our example, the manufacturing example, we'll stick with this for a little bit yet. Again here, mu, mu equals the sort of the true average length. So maybe a true average length of the manufacturing process punches the holes from the edge of the paper to the hole. And the hypotheses we're looking at are, the null hypothesis says that the mean is actually equal to 8, and then the alternative says it's not equal. So again, kind of thinking about conceptually, this is I don't need to call engineer versus if the mean is not equal to 8, then I do need to call the engineer. Okay, so if I want to, it's gonna be a big surprise to you guys. If I want to do something with if I want to say something about the population mean, what would be a good statistic that I can calculate from my data to help me say something about this population mean? Yes, so I could use a confidence interval, definitely. Again, like we talked about on Monday, that gets at the same idea, right? So I can do a confidence interval for mu, and if it contains 8, or if it doesn't contain 8, it's kind of an equivalent way to think about this problem. Sort of before we even got there, if I want to estimate the population mean, what's a statistic that I can use? So it's something that I would use for my confidence interval. Sample mean, yeah. So let's think about the statistic that I want is x bar. So again, this is what I use to calculate my confidence interval. It's what I'm going to base my hypothesis test on here as well. So we're going to want to work with the sample mean x bar and recall sort of in the setup of the problem. Back on the first page of your notes, it says we have a random sample of 25 pages from this process, which the distance here that we're looking at varies according to a normal distribution with a particular variance there. So our setup is that we have a random sample. So we have a random sample from this normal population with unknown mean mu, and for now we're going to say we know what the variance is. Okay. So if we have a random sample like this, then what is the distribution of x bar? Go back to chapter 5 here. Also normal. What is the mean of that distribution?
Mu.
Exactly right, mu. And what is the variance of this distribution going to be? That's right. So the variance, remember, is of x bar is sigma squared over n. So sigma squared is 0.1 squared over n. I guess here n is 25. Okay, good. So again, this is kind of building on what we've talked about before. So if the null hypothesis is true, so this is kind of why we have the null hypothesis set up this way. So if the population mean really is 8, then what is the distribution of x bar? If the null hypothesis is true, x bar is normal. And what's the mean of that going to be? So if the null hypothesis is true, 8, exactly right. So if the null hypothesis is true, put a 25 in there. If the null hypothesis is true, then my sample mean has a normal distribution with mean 8 and variance 0.1 squared over 25. Okay, so again, we're going to use our favorite standardization trick. So that means that a z, which is x bar minus 8, divided by the standard deviation, so 0.1 over the square root of 25, has this nice standard normal distribution that we have seen so many times now. Okay, so the only thing that's new up here is that we're saying if the null hypothesis is true, then x bar has a particular normal distribution where we know what its mean is. In general, the test statistic that we can use here is the test is z. So we'll take the sample mean and we'll subtract off the hypothesized mean, mu 0, and we'll divide by sigma over the square root of n. And just to remind you, the null hypothesis will be that mu is equal to mu 0. So in general, that's the test statistic we can use. So whatever our hypothesized, whatever's coming out of the null hypothesis, whatever we're hypothesizing this parameter to be, is what we'll actually plug in there, because that's somehow saying that the null hypothesis is true there. Okay, and this is called the z statistic. Okay. So again, the test statistic we'll use is x bar minus mu 0, sigma over square root of n. In our example, what we were looking at, we had x bar was equal to 8.0282, n was 25, and sigma was 0.1, mu 0 was 8. Therefore, z is minus 8. Which equals 1.41. So for this particular example, this is our test statistic. Okay, so again, remember this is something we've calculated this from our data, so we have some data and we can calculate it. And our goal, we haven't said how, but our goal is to be able to use this to make a decision about our hypotheses. So that's kind of where we're going next. Okay, so we'll talk about more general forms of this later, but we'll kind of stick with this example for now. Okay, so kind of coming back to our framework, we're almost there. All right, so we've done everything. We've performed the test procedure, which is we calculated the test statistic, and now we are ready to make a conclusion. So how are we going to do that? Well, this is to make this conclusion, we're going to use something called a p-value. How many of you guys have heard of a p-value before? Right, anybody who's taken stats has definitely heard of a p-value before, but a p-value is something that shows up a lot of times if you're reading a paper or a news article or something like that. You'll often see something about a p-value. Okay, so formal definition here, which might sound a little strange, but let's look at it anyway. So the p-value here is the probability of obtaining a value of my test statistic that's as extreme or more extreme than the one that I actually observed, assuming that the null hypothesis is true. Okay, so that's, again, it's the probability of getting a value for the test statistic that's at least as extreme as the one as I got, assuming that the null hypothesis is true. And so kind of intuitively, I think maybe a more intuitive way to think about this is the p-value. It's a probability, and it's going to tell me how unusual it would be to get results like the ones that I got if the null hypothesis were true. So again, we're always going to start out assuming that the null hypothesis is true. So and then see if there's any evidence to support the claim that we're interested in, right? So if the null hypothesis is true, sort of what's the probability of getting the results that I got, of getting something like I got or something more extreme? Okay, so let's think about how we can calculate this thing for our test that we've looked at here so far. So if I want to test the hypotheses that the average distance from the edge of the paper to the hole is 8 millimeters versus it's maybe not equal to 8. here's how we can go about doing this. Okay, so remember our test statistic. Z is going to follow a normal. It's following a normal distribution. So here's my standard normal distribution. You can pretend that that's the standard normal anyway. And again, the test statistic that I got is 1.41. That's the actual calculated value. Okay, and so looking at our alternative hypothesis here, when we think about again on the previous slide, let's jump back here. Again, this is the probability of getting a value of my test statistic that's as extreme or more extreme than the one that I got. So if I want values of my test statistic that are sort of more extreme than the value that I got, so I got 1.41, what sort of area under the curve there represents values that are more extreme than the test statistic that I got? Right. Yeah. So I'm interested in. I think you're both saying I'm interested in this area in the upper tail. Is that what you're? Okay. Yeah. So again, sort of more extreme. So the Z that I got was 1.41. Remember so this is sort of thinking about sort of how far am I deviating from the mean mu. That's kind of what the Z. That's what the standardization means there. So more extreme values of my test statistic would be things that are bigger than 1.41. So if I got a test statistic of 2, for example, that would be sort of more extreme than 1.41. So that's part of it. Yeah.
Would it be negative 1.41 to the left?
Absolutely, yes. So because I'm interested in a not equal to, I don't care if my test statistic is a lot bigger than 0 or a lot less than 0. Because I have a not equals to, I also need to consider this area down here, which is from negative 1.41. So those values you could think would also be more extreme than the values that I got than a 1.41. And that's because my alternative hypothesis has a not equal to in it there. Okay, so this is a two-sided alternative. So I need both tails going on here. Okay, so what these shaded areas tell me together, they are giving me my p-value. Wow, that's a terrible drawing. That these areas together will give me my p-value. Okay, and so by now, of course, we know exactly how to calculate these things. So my p-value here is going to be the probability that a standard normal is less than negative 1.41 plus the probability that a standard normal is bigger than 1.41. And by now, again, you guys all know how to use the table or your calculator to find these things out. This is, well, again, those tail areas are going to actually be equal, so this is just 2 times probability of one of them. Which is 2 times 0.0793 or 0.1586. Okay, so again, let's jump back real quick to our definition here. The p-value tells me sort of how likely or how unlikely it would be, how unusual it would be to get results like ours if the null hypothesis is true. So what I found is that the probability of getting something that's as extreme or more extreme than what I got, excuse me, if the null hypothesis is true, is about 16%. Is that unusual? So if something happened almost 2 out of every 10 times, is that unusual? It's not. It's not that unusual, right? If something happens 15% of the time, happens 16 out of every 100 times, that's not that unusual. So let's say this is not. It's not all that unusual, the results that we got. So if we had instead gotten something that was 5%, so if something happened only every 5 out of 100 times, is that unusual? It's getting more unusual anyway, right? At 1%, that's getting to be very, very unusual. So smaller p-value means sort of the results that we got are more surprising if the null hypothesis is actually true. They're sort of more unusual. Okay, but we can say something about this a little more formally here, and this goes back to. Before I move on, I did want to say something about this. Okay, so what we just did was this last row down here. When my alternative hypothesis is a not equal to, I want to consider my p-value is going to include the area in both tails, because those are both kind of like we just said. Those are sort of the more extreme, or those are the unusual values of our test statistic. And I'll come back and I'll say more about this again, but I wanted to put this up here. If you're only concerned, if your alternative simply says that your parameter is larger than that hypothesized value, then you don't care about those smaller values. All you care about is the sort of unusual values would be values that are only bigger than what you calculated. And same the other way around. If I'm only interested in knowing if my parameter is less than that value, I only care about values of the test statistic that are smaller. So the way we just calculated the p-value, very similar to how you calculate it in the other cases, but you would multiply it by 2, I guess is the point. Okay. So kind of thinking about how we can formalize our decision here, is we're going to go back to this idea that we saw back in chapter 7, this idea of a significance level, which we're going to call alpha. So we've seen that before. And that is simply the probability of rejecting the null hypothesis when it is in fact true. So here alpha is kind of thinking about what we said previously. This is kind of the value that we would see as being unusual. So is 5% unusual? Is 1% unusual? Is 10% unusual? This is the value, or this is a probability Okay, so this is something that will change. So this is something that you as the experimenter choose. So you're going to choose your significance level for a hypothesis test. Kind of what do you consider as being unusual? Is 5% unusual? Is 10% unusual? This is kind of related to the confidence interval idea, right? We had a 95% confidence interval, 99%. Similarly, you could have different levels of significance here. Okay, so we're gonna choose alpha. We're gonna choose the value that we sort of consider as being unusual. And then we can use that. We can compare our p-value to that value. So if the p-value that I calculate is less than my alpha level, then what I'll say is sort of the way to think about this is what we observed If the p-value is less than that sort of unusual cutoff, then I'm saying what we observed is more unusual than we're willing to tolerate. And in that case, I'm going to reject my null hypothesis. That's kind of how we can officially make the decision. Okay, so thinking about this again, remember the p-value, I calculated that's sort of the probability of getting something that's as extreme or more extreme than what I got, again, if the null hypothesis is true. So if kind of the way to think about it is if there's a very small probability that I actually observed what I did, then whatever my assumption was is probably false, right? So if there's a really small probability of getting something that's as extreme as what I got, then the assumption I made of the mean being equal to 8, for example, is probably not true. So then on the other hand, if the p-value is bigger than whatever my alpha level is, then again kind of it's the opposite. So then what we found, what we observed, is not unusual, and we will fail to reject the null hypothesis. Okay, so we're going to choose what your significance level is, so sort of what you think as being an unusual probability for your particular case. And then you'll compare your p-value to that to make your decision. Either reject the null hypothesis or fail to reject the null hypothesis. And then sort of, again, you can choose alpha to be anything you want, but sort of the standard alpha levels are 0.01, 0.05, or 0.10. This sort of corresponds to, again, a 99%, 95%, and 90% confidence intervals. So again, that's kind of the connection that we're drawing back there. Okay. And I run out of space here. So again, going back to our example real quick. Remember our p-value was 0.1586. And sort of a standard alpha to choose is 0.05. So if you're not told, if sort of in the context of the problem, if it doesn't say use a significance level of whatever, your default is to use 0.05. So this is your default here. Okay, so again, we want to compare our p-value 0.1586. We want to compare that to 0.05. Well, of course, 0.1586 is bigger than 0.05. So thinking from the previous slide, what does that mean? What decision am I going to make? The p-value is bigger than alpha? Yes, right. I'm going to fail to reject. I'm going to fail to reject the null hypothesis. And so that means, what does that mean if you're working for this manufacturing company? If I've failed to reject the null hypothesis, do I call the engineer? I do not call the engineer, right? So I'm saying there's not enough evidence to say that the mean is actually, I'm sort of forced to stick with the sort of the null hypothesis that says the mean is actually equal to 8 millimeters. and therefore I don't my manufacturing process isn't broken, and I don't need to call the engineer. It's kind of the interpretation there. Okay, so that's kind of wrapping up that example. One more thing to talk about before we move on to some more examples is when we're making one more thing to talk about conclusions is that again, we talked about this a little bit on Monday, that the idea sort of in a jury trial is that someone might be the result might be that they are not guilty. But what if we had more information? So if we had more information in the trial, would they have been considered guilty? So if I'd taken a larger random sample, might I have maybe gotten something that was that told me the manufacturing process was actually broken? So again, the idea is that we're always making our conclusion based on data that we have. That's kind of good science. But there's always a chance that you make a mistake, right? So in what ways can we make wrong decisions, and sort of can we sort of figure out how often that's going to happen? And this leads us to the idea of errors in hypothesis testing. So again, at the end of the day, from our hypothesis test, we make a decision. We reject the null hypothesis, or we fail to reject. And for either of those decisions, again, the truth those could be correct or they could be incorrect. And so this leads us to this idea of error. Okay, so a type 1 error consists of the first type of wrong decision that we can make, which is rejecting the null hypothesis when, in fact, it's true. So it could be true that the manufacturing process is actually not broken, but I might reject the null hypothesis and say that it is broken, and that's a type 1 error. So if my decision is that I've rejected the null hypothesis, but the null hypothesis is actually true, then that's giving me a type 1 error. And maybe let me fill in on here real quick. So if I reject the null hypothesis and the null hypothesis is false, well, that was the correct decision. And similarly, if I fail to reject the null hypothesis when it's true, that was also the correct decision. Okay, so my first type of error is if I reject the null hypothesis when it's true. Second type, we'll call this type 2 error. That's lots of double negatives going around here. So that means I'm not rejecting the null hypothesis when I should have. So the alternative is actually true, but I have failed to reject the null hypothesis. So that is going to be our type 2 error. These things get really confusing to try to interpret. Okay, so anyway, these are the two types of wrong decisions that we can make, and so let's write down a little bit more about what these are. So again, thinking about this table, you would hope to have a small. You would want there to be a small chance that you make an error, right? So I want the probability of a type 1 error to be small. So I want there to be a small chance that I reject the null hypothesis when it's true. And I also want there to be a small chance, ideally, of failing to reject when it was false. And so that's why we want to think about the probability of observing these or of making these errors. So the probability of a type 1 error, this is just alpha. This is our significance level. And again, that's something that we can set. So whatever I choose my significance level to be, I want that to be small. I want the probability that I reject the null hypothesis when it's actually true to be small. So given that the null hypothesis is true, the probability that I reject that, I want that to be small. So maybe 5% is a small probability there. So the other error, type 2 error, again, when the null hypothesis is false, but I want the probability of failing to reject it when it is actually false. So the symbol we'll use for this is a beta. and this is equal to something called 1 minus the power of the test. So what is the power of the test? Say more about that. I'll say more about that later. So this is something we can calculate this. We'll say stay tuned. We'll talk a little bit more about that later. Okay, so to think about what these sort of put these errors in words here, let's finish up with this example here today. This is out of your textbook. So before agreeing to purchase a large order of polyethylene sheaths for a particular type of high pressure oil filled submarine power cable, the company wants to see sort of strong evidence or conclusive evidence that the true standard deviation of the thickness of these things is less than 0.05 millimeters. So we want this manufacturing process to be very, very precise. So let's kind of practice part of what we've talked about here today. So what hypotheses should I test, and then what are the corresponding type 1 and type 2 errors? Okay. So what is the parameter that I'm interested in testing here? The thickness? What about that thickness? Yeah, so I want to know something about the true standard deviation of the thickness of these sheaths. So that is our standard deviation sigma. So my null hypothesis is going to be sigma equals something, and then my alternative hypothesis is going to be also involving sigma. Okay, so what number do I want to throw into my null hypothesis here? The claim that I'm trying to test is that standard deviation equals what? 0.05 exactly. Okay. So then I can always put that same number into my alternative hypothesis. So 0.05 millimeters also goes over here, and I just need to fill in the inequality or sign there. So what symbol should go in my alternative hypothesis? So I'm either interested in the claim I want to make is that the standard deviation is equal to 0.05, but what am I interested in testing? Yeah, so what I want evidence of is that the true standard deviation is actually less than 0.05. So the claim that I want to test, or what I want to see if there's evidence for, is my standard deviation less than 0.05. So that's kind of what I'm interested in knowing at the end of the day. So we'll start out assuming that the standard deviation is actually 0.05, but what I really want to know is it less than 0.05? Okay, so with these hypotheses in mind, what are my sort of inwords here? What are my type 1? And then what is my type 2? Okay, so again we have our terminology here. So the type 1 error is I'm rejecting the null when it's true. So in the context of this problem, what does that mean? So what the type 1 error, if I make a type 1 error, what that means is that the standard deviation really is really is 0.05. So the null hypothesis is actually true, but I conclude the wrong thing. So I conclude that it's less than I conclude that it's less than 0.05, and again, so if it's less than 0.05, then I'm gonna make this purchase. So then it's less than 0.05, and I make the purchase. So if I conclude that the standard deviation is small enough, I'm going to go ahead and make this purchase order. So type 1 error means that the null hypothesis is actually true. The standard deviation is 0.05, but I conclude the wrong thing. So I'm saying it's less than that, and then I'll go ahead and the result of that decision is that I'll go ahead and make the purchase. Okay, so that's the type 1 error. Type 2 error, again, the null hypothesis is false, but I fail to reject it. So what that means here is that the standard deviation is actually less than 0.05, but I conclude that it's equal to 5 to 0.05. And again, if the standard deviation equals 0.05, I want it to be less than that to make the purchase, so therefore I do not make the purchase. All right, so let's say that you are let's say you work for the company that wants to buy these things. Which type of error do you really not want to make? If I'm the company that's buying these things, which is the type of error that I don't want to make? I don't want to make a type 1 error, right? I don't want to make the purchase based on the wrong information is kind of the idea. So I need that standard deviation to be less than 5. I need the manufacturing process to be really precise. And so I conclude that it is really precise and I make the purchase when in fact it's not actually as precise as I need it to be. So if I'm the company buying those things, type 1 error is really bad. Type 2, again, I won't make the purchase, but it's sort of like I haven't gotten defective products is the idea. So maybe I'll need to shop around and find a different place to buy these things, but I sort of I'm not making that's not the worst decision for me. However, if you're the company that's manufacturing these things, it's the other way around, right? You don't want the people who are buying your product to wrongly conclude that your manufacturing process is not precise enough, and therefore you're going to lose that business. So different types of the error is more serious depending on which side of this thing you sit on. But anyway, I think this is a good place to finish up. I do have your exams to get back to you guys, so come on up and get those. And yeah, otherwise have an excellent day. Okay. Here's A through L, and here is M through Z.